Let me tell you a little bit about myself real quickly. I've always been very interested in space. I pursued a master's degree in physics and space technology from the University of Leicester. And when I graduated, I worked for the British government for 3 years in radar polarimetry, and came over to the United States in 2002 to pursue a PhD in theoretical physics. But my real interest has always been in space, and I'm very, very aware that current technology severely limits our exploration capacity beyond the solar system. And I've always tailored my thinking in theoretical physics to how we can potentially apply this to new and advanced propulsion paradigms. So, what I'm going to talk about today, I think it's very important, before I introduce my idea, to talk to you a little bit about the fundamental ingredients. So I'm going to be talking about the cosmological constant, which is fundamental to the understanding of the idea. I'm also going to be saying a few words about vacuum energy, brains, supersymmetry, and then I'm going to introduce the main idea. But just really to put things in perspective, the space shuttle has a maximum speed of around 10 kilometers a second. And when we look at this chart on the x-axis, it's a logarithmic scale, so we have Earth at 1 astronomical unit. Take us about 3 or 4 days to get to the moon, about 9 months to get to Mars. And we see on this logarithmic scale we've got Saturn at 10 astronomical units, the heliopause at about 100 astronomical units, and Proxima Centauri, or Alpha Centauri on this chart, which is the closest star, about 4.2 light years away, is somewhere between, it's somewhere up here. And using the space shuttle, it will take on the order of 50,000 years or so, and that's just to reach the closest star. So we're severely limited in our exploration of the galaxy at the moment. And not only that, but rocket technology is over 1,000 years old. The Chinese invented it around about the 10th century, a little bit for entertainment, for fireworks, and they also use it as rocket artillery. So, I want to say a few words as well about the current state of breakthrough propulsion. People have been thinking about this for a few years. NASA actually formed a breakthrough propulsion program, ran for about 6 years, and in Britain we had Project Green Globe, British Aerospace, and the topics of interest were these sorts of ideas of warp drives, wormholes, and the potential for reaching previously inconceivable velocities. So let's talk about the ingredients. The first ingredient is understanding the cosmological constant. This is Einstein's field equation, and it relates the geometry of space-time to the energy and momentum content of space-time. On the left we have the Ricci scalar, the Ricci tensor. This encodes the geometry of space. And this is fundamentally connected to T mu, the stress energy or the energy momentum tensor, which describes the content, the matter-energy content of space-time. When Einstein solved his field equations, he actually discovered an expanding universe. Now, 2020 vision, hindsight, now we know that the universe is expanding. But he liked the idea of a static universe. He didn't like the fact that his equations would fit in an expanding universe. So he added a fudge factor, this lambda term on the left-hand side, known as the cosmological constant. And its addition to the equation was to ensure that the universe was static rather than expanding. You've probably heard of Einstein talk about his biggest blunder. It wasn't that it was a mistake. The mistake was him not appreciating that his equations predicted the universe was expanding. So this is the cosmological constant. Like I said, we now know the universe is expanding, but lambda still has a very important place in cosmology because when we look at observations, when we look at how fast the universe is expanding, we can use the cosmological constant again to fudge the equations to match observation. Now, this lambda term, we need to understand what it is. We can't just say, okay, there's an extra term. Let's try and understand fundamentally what a cosmological constant is. Now, by far the most successful theory of theoretical physics is quantum field theory. And it's been verified for the last 5 decades in particle accelerators. And one of the fundamental ideas in field theory is that every point in space consists of a harmonic oscillator, and the certain vibrational modes of this oscillator in some way represent the fermions and the bosons that we see in the universe today. So, going by this paradigm, we also know from quantum mechanics that no field oscillator can be completely at rest, and this is the origin of what we call the 0 point or the ground state fluctuations. And these oscillators have an infinite degree of freedom, namely their frequency can span from 0 potentially all the way up to infinity, but we impose some kind of cutoff. So when we use field theory to calculate the ground state energy of the universe using this equation, this comes essentially from E squared equals C squared P squared plus M squared C to the 4 Einstein's formula. Set CNH bar to 1, which physicists like to do. Without going into too much of the details, quantum field theory predicts the ground state of the vacuum to be 10 to the power of 71 GeV to the 4th power. Now, experimental data gives us this number, 10 to the minus 47. So we're hugely off. Using the most successful theory of physics today, we predicted something that's 118 orders of magnitude incorrect. And it's been known as the biggest blunder in physics today. So we have a conflict between field theory and the small lambda. So is it possible to account for the cosmological constants still using the ideas of field theory? And it turns out that we can, but we have to add a few extra ingredients. We have to add supersymmetry, we introduce extra dimensions, and we can start talking about the Casimir effect. So let me very quickly say a few words about each one of these. One of the pathologies of renormalizable quantum field theories with scalar fields, namely the Higgs field in quantum field theory, in the standard model, is that they predict infinite masses. What we find is when we calculate the mass of the Higgs, the one-loop corrections give us infinities. We can actually tame those infinities by supposing there exists a kind of mirror set of particles known as supersymmetric particles. For example, for every quark, there's a squark. For every gluon, there's a gluino, and so on and so forth. Now, the addition of these supersymmetric particles to the Lagrangian also add infinities, but fermions add infinities of a negative sign. So the quadratic infinities of the supersymmetric partners cancel out the positive infinity coming from the Higgs field. And so we can go from 10 to the 71 GeV to a ground state of the vacuum of 0. So this is getting a lot closer to the 10 to the minus 47. So now we're on 0, so we've just got to notch that up a little bit. So this is where supersymmetry comes to help tame the bad prediction of field theory. I'm sorry. Now, now we're going to go on to say a couple of words about vacuum energy in extra dimensions. Extra dimensions aren't a new idea in physics. They first popped their head in the 20s when Kaluza and Clyde tried to unify gravity and electromagnetism. And they've been cropping up, and it's very popular today. M theory, we currently believe that's possibly the grand unifying quantum theory of gravity is set in 11 dimensions. So the idea of extra dimensions isn't anything new. Another ingredient we need to understand to start talking about this propulsion idea is the Casimir effect. Now, I mentioned earlier that each point in space is an oscillator with an infinite degree of freedom in terms of its frequency. And Heinrich Casimir in 1954 in the Netherlands predicted that if you put two parallel conducting plates in the vacuum, you would exclude certain modes from certain modes of the 0 point oscillation from existing in the vacuum. You'd only have these kind of resonances occurring. But there's no such exclusion on the anterior of the cavity. And what this creates is a kind of pressure gradient that pulls the plates together. And this has been demonstrated in the lab to within 1% accuracy by Lamoureux recently at the University of Washington. So we're very confident on the reality of the 0 point fluctuations. The last ingredient, and this is the most important ingredient, is the chain and glue model, which is an extension of a very popular idea in physics at the moment, the ADD model, Arcani-Harmonic-Diwali-Demopoulos model, which supposes that our universe is a 3+1 dimensional brain with an extra toroidal compactified dimension. And the standard model gauge fields, namely the weak and strong nuclear forces and the electromagnetic force, are free to propagate in our brain Gravity, or rather the graviton, is free to propagate in the brane and the extratoroidal dimension. And the purpose of introducing this extra dimension was to try and explain what we call the hierarchy problem, the current weakness of gravity when compared to the other forces. And in a sense, the way you can think of this is that gravity is diluted because it has freedom to propagate in extra dimensions. And what they found, Chen and Gu in their paper, there's, when you put all these ingredients together, that we have this imperfect cancellation of vacuum energy in the extra dimensions. And this, they suppose, is what's responsible for the low but non-zero cosmological constant. Their equations, their ideas go roughly like this. The first equation is a very standard calculation in Casimir energy. You calculate the Casimir energy at radius r, you take it off to infinity, and that gives you the renormalized vacuum energy. And when you plug in for the graviton and gravitino, which are the only fields that are free to propagate in the extra dimension, Chen and Gu found a relationship between the Casimir energy, or I'll say the vacuum energy. They found it was related to 1 over a squared, where a squared is the radius of the extra dimension, and there's a couple of constants in there. So that's really fundamental to understanding my idea. So they say that Casimir energy can be identified as the source of the cosmological constant, and this is intimately related to the size of the extra dimension. So let's review very, very quickly. The cosmological constant is intimately related to the size of the compactified extra dimension. Now, how can we relate this to exotic propulsion? The perspective I came from in my paper were what constraints do the laws of physics place on the abilities of an arbitrarily advanced civilization. This was in the same spirit as a paper on wormholes that came out about a decade and a half ago from some very, very eminent physicists. So, the essential idea, it was inspired by the Alcubierre warp drive. Where he essentially said, okay, let's expand the space-time behind the spacecraft, contract the space-time in front of the spacecraft, and this can create a kind of propulsive mechanism. And the angle that I was coming from was, okay, so if we relate the cosmological constant to the radius of the extra dimension, what if it was possible to locally alter the radius of the extra dimension in the vicinity of a spacecraft? Namely, reduce the radius of an extra dimension at the rear of a craft, increase the radius of the extra dimension in the front of the craft, thereby creating a kind of gradient in the cosmological constant, a kind of a localized contraction and an expansion. Now you might be thinking, okay, how do we alter the radius of an extra dimension? Now, brane gas cosmology is a very important part of string theory at the moment, and they're trying to understand why the universe has 3 large spatial dimensions and 6 or so compact extra dimensions. And the current thinking is that strings, in effect, wind around these extra dimensions and stop them from expanding. So if we could somehow stimulate or directly interact with a string, we may, or maybe not us, maybe an arbitrarily advanced civilization, hopefully us, we may be able to find a way to locally alter the value of the cosmological constant. Now, what I've got for you is a few calculations. Very back of the envelope, by no means exhaustive, but I think it's interesting to throw some numbers out there. So let's have a look at the current value of Hubble's constant. Now this is intimately related to the cosmological constant. They're linearly proportional to each other. Hubble's constant says that space-time is expanding at 70 kilometers a second per megaparsec. Now this is actually easier to understand if you convert this into SI units. 2.17 times 10 to the minus 18 meters per second per meter. What's that telling us? It's telling you that a meter of space-time, if you sat for 2 billion years, space-time would stretch from 1 meter to 2 meters. That's the way you want to understand the cosmological constant. Now, what we want to do is bring that up. We want to expand space-time, not a billionth of a meter a second, but let's pump that up to the speed of light and see what would happen, under the paradigm of how much energy we would have to put in and how would we have to alter the radius of the extra dimension. And remember, this isn't a problem. Nothing can travel through space-time at the speed of light, but there's no restrictions on the inflation of space-time itself, and that's what we're directly doing. Okay, Here's some basic relationship. So earlier I demonstrated that the Casimir energy, four-dimensional Casimir energy, can be identified with a cosmological constant, which is intimately related to 1 over the radius of the extra dimension squared. So we can form some basic ratio relationships, and the subscript C is, okay, let me take what I want the cosmological constant to be. I want, Hubble's constant, I want that to be the speed of light, so that's why I've given it the subscript C. And I can form this sequence of relationships based on these results from earlier. So what we want to do, we want to take Hubble's constant, talk about the speed of light, and it was originally this value, and so essentially what we need to do is increase Hubble's constant by a factor of 10 to the power of 26. Now, let's have a look at how much we would have to constrict an extra dimension to actually achieve that. Plugging this into the ratio, now we don't know the size of an extra dimension, but in the ABD model which I'm working in, they suggest that the extra dimension could be as large as 1 micrometer. Why haven't we seen it? Remember, only the graviton is free to propagate in the extra dimension, so we can't see it. So that means we would need to shrink the radius of the extra dimension from 1 micrometer down to 10 to the minus 19 meters. And this would locally create an expansion of space-time at the speed of light if we were able to do that. Another interesting calculation is how much energy would be required. Now, when you figure out the cosmological constant in SI units, it's around about 1/20 billionth of a joule per cubic meter. Remember, we want to increase this by a factor of 10 to the 26. And so that would, we would need to increase the energy in space-time to 10 to the 16 joules per cubic meter. Now let's say we have a spacecraft. We want the entire volume that a spacecraft exists within, we want that space-time to expand. So let's multiply by the volume of a spacecraft to find the total energy. Just plugging in some numbers, like I said, back of the envelope calculation, 10 by 10 by 10, something the size of maybe Apollo, would give us a total energy requirement of 10 to the 19 joules. A lot of energy. But while we're talking warp drives, let's think about what the most effective way to create energy is, the most efficient way of generating energy. It's matter-antimatter collision. It's 100% efficient. So were some sufficiently advanced technology able to utilize antimatter, this would correspond to about 100 kilograms of antimatter, which is not, at the moment we're creating trillions of a gram in particle accelerators, but let's extend that. At least we can create it. So we need about 100 kilograms of antimatter to achieve that. So this is the picture. We have a spacecraft. It's somehow able to, perhaps using antimatter or some other exotic energy source, it's somehow able to directly interact with a string, manipulate the radius of an extra dimension to create locally a bubble of expanding space-time behind the spacecraft, contracting in front, essentially taking us further away from our starting point and bringing us closer to the destination. Let's look at some fundamental limits. I think this is quite interesting as well. We said earlier the radius of the extra dimension was about 1 micrometer. Now, there's a limit to how small this extra dimension can be if, in actuality, it's the string that's wrapping around it. A string is it's on the order of the Planck length. That's about 10 to the minus 35 meters. So that places a fundamental limit of how small we could squeeze the extra dimension to be. Going back to these ratios that I talked about earlier, and plugging in R over R min, what we'd find is that the ultimate limit would be 10 to the 32 times the speed of light. Again, very back of the envelope style calculations, but interesting, because I've never seen any predictions on any paper that says that there's what the ultimate speed limit would be. But under this paradigm, that the vacuum energy is related to the radius of an extra dimension, and how small could we ever make an extra dimension? Well, about the string scale, this would put a fundamental limit on how fast we could travel. And then plugging that in, we would require an amount of antimatter roughly equivalent to the mass of the sun, squeezed into a volume of 10 by 10 by 10. So, obviously some very difficult technological things that we have to achieve, but I think it's fun to throw some numbers out there. Okay, some obvious questions. We don't know that supersymmetry exists. We've never seen a selectron, a neutrino, a squark, or anything like that. But it's a very popular idea in physics because it solves these renormalization issues with the infinite Higgs condensate. Are high dimensions real? Again, we don't know, but they've been cropping their head up for about the last 80 years in physics. So, but that's not the question. And again, how could we focus this energy to directly stimulate a string so that we could either contract it or expand it for our technological purposes? So there's a lot of questions to ask. But this year, the LHC is opening, the Large Hadron Collider in CERN. And it may be able, it can reach energies of about 2 TeV. It may be able to detect supersymmetric partners. We may get indications of high dimensions. So perhaps that will answer some questions. So just to summarize, the ideas of warp drives aren't new. Alcubierre in 1994 came up with an idea, but no one's really hit upon, how do we create this warping of space and time? The metric has been demonstrated, the principle has been demonstrated, but no one's really said how can we do this. So this is really a novel idea of how we could create this local expansion and contraction. And all previous theories have been based on Einstein's theory of general relativity, but this is the first propulsion concept that I'm aware of that's based on a quantum field theory that incorporates high dimensions, supersymmetry, and so on and so forth. So, just in closing, I want to say thanks to my supervisor, who's not absent, who gives me the freedom to pursue these academic things. Glenn Robertson for inviting me, and I just discovered today Eric, who was responsible for getting me here. So, thanks very much, everybody.
Does deep brain theory assume any spin-orbital structure on the manifold and bulk?
There is a spin-orbital structure, but this isn't taken into account. I mean, we're just using very elementary superfields here, which commute, which give us the necessary vacuum ground state at 0.
Okay, because that's going to lead to the connection of the, depending on the sign of the Casimir force in the bulk is going to depend upon the fermionic and bosonic degrees of freedom.
And that's very important.
Especially
too. And that's very important too, because the sign of the Casimir force is going to be directly related to whether we can expand or contract. And if we had some control over both, then perhaps a shifting in the Casimir sign and understanding of that would be very important.
Okay, I just wanted to make a comment.
What is the ultimate speed for a warp drive based on how?
Based on this, 10 to the 32 times the speed of light.
Pretty good sporting.
You could probably cross the known universe in maybe a few thousand years.
Would the energy requirements drop if you started out with a smaller? I only realized this equation after I've done some calculations. What if you go from 1 micron down to a smaller size?
Exactly.
Does this minimize the energy requirements?
Yeah, exactly. That's a good question. I'm glad you raised it. 1 micrometer is the absolute biggest the extra dimension can be, because we've tested gravity down to just below that level.
Sure.
So 1 micrometer is by far the highest it could be. If it was smaller, then the correct it would reduce the overall energy.
What about 10 to the minus 17th meters?
I would have to do the calculations, but...
I was looking at your picture to say about the region of space, about the region of space about the spacecraft.
Yes.
And I'm going to ask a very naive question, but it's just that I'm thinking in terms, how do you know that you'd have something that would be relatively homogeneous about the craft? Because it just as you didn't take care of that, you'd have stretch and shear forces.
Certainly, this is a very primitive theory that's in its early stages, and I just wanted to demonstrate the idea, demonstrate the principle. The idea is that we would be able to kind of...
Yeah, but the reason I was asking is because that the reason I asked is you looked at the Hubble constant and you had an hc over h, and you had something like an enormous, the hc
10 to the 8, which is what we would like to put the Hubble constant
right.
up to, divided
by
by its value.
That's equivalent to what you might call early universe inflation, which
certainly, certainly.
It's almost completely equivalent. But when I'm thinking is you're looking at the ship, and you have some sort of a bubble or something like that, is that you'd better not only think in terms of the boost, you better think in terms of the relative homogeneity requirements, because otherwise you're going to twist, shear, and rip ship.
No, I agree. I mean, a perfect scenario would have a flat region, very much like the Alcubierre bubble would have a flat region of space-time surrounding the craft and create this kind of local.
Well, that's where I have my disagreement, because if you have something that intense in a localized area, you're going to start having curvature effects. And if you don't take care of the curvature effects, you're going to shear the ship apart in no time flat.
Yeah, exactly. Yeah, exactly. Question?
Energy density.
Yes.
You mentioned that you can bring that extra dimension down should it exist by boosting the energy density. I'm a
Exactly.
little confused, I'm afraid, if you help me out, when you talked about the energy density of space-time, and can that be synonymous with mundane energy density?
Yeah, exactly. I mean, this model is based upon the Chen and Wu paper, which identifies the Casimir energy in the extra dimensions, or rather, the addition of the supersymmetric fields, and then you calculate the Casimir energy. This identifies this with the cosmological constant. So I'm building on that model.
Gotcha. So if you ramped the energy density locally, you could directly affect the size of that extra dimension. Is that what the theory is?
In essence, yeah. This is the idea exactly. You hit the nail on the head. Any other questions?
Or concerning the momentum conservation law, in that case, how do we think?
How do we think?
Regarding the momentum
momentum
conservation law.
Maybe we can talk afterwards.
Pardon?
Maybe we can talk afterwards. I didn't understand the question.
What is the
Momentum conservation.
conservation?
Momentum conservation.
Okay, momentum conservation. Because we're directly working with the expansion and contraction of space-time, I don't think that's necessarily going to be too much of an issue. We're not pushing a spacecraft through space-time, so we're not talking about the classical laws of physics.
I was just going to ask you, just if you could go back to the equation for deriving the energy requirements based on the size, the size shrinkage.
Yeah, this one?
You mean the dimension shrinkage?
The dimension shrinkage.
How much energy you
How
need
much
to
is
shrink
for the
the
dimension shrinkage?
This equation?
Okay. So 10 to the minus 13th. And the 10 to the minus 13th then becomes
Oh, exactly. 10 to the 26 square root.
10 to the 26 square root.
Exactly.
And then the energy was then calculated by a compression kind of an energy?
Simply, good question. Simply by looking at the value of the cosmological constant now, by seeing what factor, how we have to raise it to, and by just a sequence of ratios exactly, and by identifying that with how much energy would have to be, put into a string to compactify the dimension. But,
Okay, thank you.
Okay. Well, thank you very much again.
We get one more.